So hopefully you have an idea of what solving systems of equations means now, and you have both a visual representation of it, in other words, that it's really this point right here when on these two lines, and then just the literal interpretation of it being that we have two equations and there's only one exact set of values that will make both of these equations zero. There's lots of values that we could fit into this equation as individually, and there's lots of values we could fit into this equation individually. But in order to make plug in values where they would work in both of these equations, we kind of have to do some work. And so there are two primary methods of solving systems of equations. One we've already done. I mean, one of them you could see, well, what if I just graphed a line and then saw where they intersected? That would totally work. You could do that at any point to solve a system of equations. But what if I don't want to take the time to graph a line? What if I want to do it a little bit more quickly? Well, there are two primary methods, and the first is substitution. Okay, and you use substitution all the time in other places in math, and you've used it before. But when I'm going to use substitution, I want to be able to convert an equation into some type of equation that I can then use to substitute, right? So here, I don't have this equation in terms of x or y. So the first thing I need to do if I'm substituting is I need to solve one of the equations to be in terms of either x or y. So I'm going to take this equation here, and I'm going to get it in terms of x. And what I mean by saying I'm getting it in terms of x, I'm going to solve this equation for x so that x is on its own side. So clearly, to be able to do that, all I need to do is to add a y to both sides. If I add y to both sides, it'll get rid of it on this side of the equation, and all that will be left over here is x. And if I do that, you should be able to see that that's going to become x equals y plus 1. If I get x by itself and I add a y to both sides, then all that will be left on this side of the equation will be x, and that y will be moved over here. Why did I do that? Well, now, what this means is, right, this equal sign implies that these two things are equivalent, that x is the same as y plus 1, that whatever y is, I add 1 to it and I would get x. So anywhere that I see an x in my other equation, I can plug in or substitute a y plus 1. Since x equals y plus 1, since those two things are equivalent, I can substitute a y plus 1 in for all x's in my other equation. So I'm going to do that right down here. So if I do that, this would become y plus 1, and I'm just going to put it in parentheses because that's probably the safest way to do it. And then plus y, that y is still there, equals 3. So what I've done is I've taken this equation and I've rewritten it where I plugged in y plus 1 in for x. And then this is a solvable equation. There's only one unknown, and that unknown is y, so I can actually solve this. So as you can see, if I simplify this side, I need to add the y's together. That would become 2y plus 1 equals 3. And then I would need to subtract 1 from both sides, and when I do that, I will get 2y equals 2. And then I would need to divide both sides by 2, and I should get that y is 1. And there you have it. We already knew that, but this is just another way to solve it. So now how could I go back in and solve? Well, I could just plug it in here. If I know that y is 1, then x minus 1, because y is 1, will equal 1, and I can solve for x. And so all I need to do is add 1 to both sides to get x by itself, and x is 2. So that is the substitution method. I'm going to solve one of the equations for x or for y and then substitute back into the first equation or the other equation. The other way to solve these is with this method called elimination. And elimination, how you can think of it is that I'm actually going to be adding these two equations together from the top down. So I'm looking this way and I'm going to be adding down. So if I add an x plus an x, for example, if I add x plus x, then that would become 2x. And look at this. If I add a positive y to a negative y, what does that become? Well, that just becomes 0, and there's nothing left over. And then when I add 3 plus 1, that becomes 4. And then I would solve this for x, and obviously x is 2. And then once again, could go back and plug in x to either of these equations, and then I would get that y equals 1. So that's elimination. Now, here's the thing. Sometimes these problems aren't always going to be this simple. Sometimes I'm going to need to do some work in order to eliminate. So let's say, for example, that instead of Why did I add them together? Well, I added them. What this allowed me to do is it allowed me to eliminate these terms because they were exact the same amount and they had the opposite sign. There was one y here in both cases. One was positive and one was negative. Well, what if instead of, I don't know, x plus y equals 3, what if it said 2x plus y equals 3, and then x minus 2y equals 1? Well, the first thing you should say is this is probably a better candidate to be using substitution to solve, because you could see very easily it would not be hard to solve this equation right here for x very easily. I could just add 2y to the other side. I would get x, this equation in terms of x, and then I could substitute into this equation. But what if I forced you to do this equation, to do this system by elimination? This time, if I were to add these two equations together, nothing would eliminate that easily. I would have to do some work in order to make that happen. So, for example, these y's do have the opposite sign, but because it's 1y minus 2y, I would still have a negative y left over. So I'd actually have to do some work to this top equation to make it be able to be eliminated. So what if I multiplied that entire top equation by 2? Well, then, I'm going to come down here, then this would become 4x plus 2y equals 3. Oh, I'm sorry. I actually have to distribute this to every one of these terms. I almost made a very common mistake. So that wouldn't be 3. That would become 2 times 3 is 6. And then this, I haven't done anything to this bottom row, so this would still be x minus 2y equals 1. And now I can eliminate, right? Now I have two terms that have the same amount and have the opposite sign. So when I add them, they would now cross out. Those would go away, and I'd have 4x plus x, which is 5x. And I would have 6 plus 1, which is 7. And that is not right. Let me see here. I did something wrong. I need to go back and check my work. So this would be 4x plus 2y equals 6. That's right. Oh, no, this is right. This is right because it's a completely different example. And then I would solve this, and I would get that x is 7/5. So that's right. Okay, so I use this to point out, and then I could go back, plug this x in either of these equations and get y. I use this example to show you that sometimes in order to eliminate, to use elimination, you're going to have to do some work first to get two terms with opposite signs but have the same amount. And the key here is that when we did this work, we were trying to get this here to be a 2 so that we could eliminate these. So here's what I want you to do. Last page in your notes, I want you to go here to this problem. And I want you to solve this system of equations using both substitution and elimination. So one time I want you to go through and try and solve it using substitution, and it's going to be really hard. And then another time I want you to go back and use elimination. But I want you to try and use which one you think would be easier first. Okay, so solve these using both substitution and elimination, and then we will pick up from there in class tomorrow. Thank you.